Morning, students. Today we will be discussing about the nitration, halogation, and oxidation. So, our topic will be enlightening the organic chemistry, medicinal chemistry, and even pharmaceutical chemistry. This is related to the different chemical aspects. So, we should first of all we should electric substitution. So, electrophilic aromatic substitution is a fundamental type of reaction in organic chemistry where an atom, usually hydrogen on an active tail, is replaced by an electrophile. General mechanism in following step. That means in case of chemical reaction, any atom or any hydrogen that is reacting with the aromatic tail. So, first of all, the steps are followed like the generation of file, attack on the pi system, and proton removal and reactivation. First of all, the electrophile. File means what? File means searching. So, electrophiles means electron loving. That means they are having the tendency towards the negative ion or the negative pole. So, that means they will be having the positive charge. So, the electrophile, that is the E plus, is known as the electrophile, is typically generated C2, the reaction mixture from a suitable agent. So, electrophile will be having a positive charge. They will be having a tendency to react with the negative ions. So, attack on the Pi system. So, we know in case of aromatic carbon, there are unsaturated double bonds. So, that unsaturated double bonds having lots of electrons, that's having lots of electron. So, they are trying to attack on that electron bonds. So, the pi system that is considered as the two electrons are parallelly making a bonds. So, there will be reaction of the electrophile. This forms a resonance stabilized carbocation intermediate called a sigma complex or a aranium. So that will form the electrophile and the reagents or the reactant where it will be reacting. They will forming a carbocation. The aromaticity of the ring is temporarily described is disrupted in this step. As a result, whenever the electrophile will be acting in the aromatic ring, as a result, their aromaticity will be somewhat disrupted. Proton removal and rearomatization. Then a base removes the proton from the carbon bearing the electrophile in the sigma complex. So as a result, the proton at this condition that will be removed, and the step restores the aromaticity of the ring and building the substituted aromatic. As a result, what happens? The product will be stable and the excessive proton will be removed. Okay. As a result, the aromaticity will be again revived. Next, the mechanism of the electrophile, you can see. Now you see the mechanism of electrophilic aromatic substitution. Step 1, the electrophile attacks the pi bond of benzene by pi and electrophile to form a carbocation. So this is the electrophile P plus, and the benzene ring contains the electronegative part, that is the containing pi system, where it will be attacking, and it forms a carbocation. Cation means the positive ion containing part. So as a result, it will be having this positive ion. Step 2, the depolarization of the carbocation to restore its aromaticity. As a result, the positive ion will be trying to release their photons to become stable. As a result, it will be reacting with the base or any negative part. As a result, it will form a substituted benzene, and HB, the base will be jet. Now, there are different type of electrophilic substitution like nitration, halogenation, and oxidation. So, in case of nitration, this is aromatic carbon. Then the nitro group that is forming from the HNO3 H2SO4, and it forms ARNO2 aromatic benzene like this, or nitroaromatic. In case of sulfonation, again the SO3H will be liberated and it is containing SO3H minus. That will be reacting with the aromatic carbon ArSO3H, aromatic sulfonated sulfur. Halogenation, the halogen reacted like X is represented the halogen, the oxygen, and so they will be forming an aromatic like nitrobenzene, fluorobenzene, bromobenzene, and along with HCl or HBr or this type of compound acid or HF can be formed. So there are another type of Friedel-Crafts alkylation that is in presence of an halide RX, that is the CH or CH3 along with the aluminum chloride, they will form aromatic ethyl CH C6H5 toluene. This type of any R group may be like CH3, C2H5, LH2, LH2, different group. So alkyl is replaced the benzene. Now, Friedel-Crafts alkylation, there are different varieties. So, from different aromatic like RX or the hydrogen can be different and it forms different type of aromatic compound along with different hydrogenous compound. Depending upon the quantity and the desired and produces. Now going to direct the reactions. HNO3H2SO4 produces nitrobenzene, sulfonic acid, benzene sulfonic acid, then with bromine and iron, bromobenzene, then methyl bromide, presence of aluminum chloride, it forms methyl benzene. Okay. Then toluene. In case of toluene, they can be also reaction like the HNO3H2SO4. They forms the paratoluene benzene and toluene sulfuric acid, bromotoluene. So they faster than the same reaction with the benzene. So it is already toluene having the more reactivity than a normal benzene. Next we are going nitrobenzene. So this nitrobenzene also forms different type of meta-dinitrobenzene, case of sulfuric acid, nitrosulfuric acid, chloronitration, chloronitrobenzene. These are slower than the same reaction with the benzene. So they are having the smaller reactivity. Okay. So substitution on a benzene ring affect aromatic substitution reaction in two ways. How the substitution going on? They are depending on factors. One is reactivity, one is orientation. Reactivity is activate faster than the benzene. First, they activate the benzene ring, or they can deactivate. Like in case of toluene, the toluene can activate the benzene ring. In case of nitrobenzene, nitrate can deactivate the benzene. So the reaction will be slower. Orientation. So some of the, but they are ortho and para directing, and some of the that is meta directing. So depending upon the chlorine or any other substitution will be in the ortho or para or maybe in the meta position. Now it you can see the CH3 methyl group that activates the benzene towards the electrophilic aromatic substitution, and it directs the substitution at the ortho and para substitution. Suppose that is containing benzene along with the CH3 that is toluene. If a substitution is there, they will be in ortho or in the para position. Okay? But in case of nitro group, that will deactivate the benzene ring and then direct the substitution of meta position. So that's why you have seen the meta dinitrobenzene. So these are the common substituent group that effect on IAS. Like some of the compounds that is amine group, okay, and OH, OR, NHCO, CH3, C6H5, they are orthopara directors. And in case of meta director, there is the aldehyde, acetaldehyde, and sulfonic acid, CWH, acetonitrile. These are the meta directors. And the increasing reactivity. In case of nitro, NR3CA, CWH, the reaction rate is not so much faster than the which are NR2 groups. Okay. Now you can see the reactions. Here the reaction rate is described here. Now, if there is more than one group in the benzene ring, the group that is more activating higher on the list will direct the next substitution. That means you can follow the series here, which is having the more higher activity. They will direct towards the electrophilic substitution. Order is important. Synthesis of meta nitrobenzene of benzene. So suppose how can you prepare it? Benzene ring, you have to nitrate it and nitrobenzene, plus of propane and bromo nitrobenzene. So nitro group produces the beta reduction. So that is the 2, 3 bromo nitrobenzene. Since this is a para bromo nitrobenzene here, the first react the bromine, then you produce the halogenation H2SO4. So there are chances of formation of two products, ortho nitrobenzene or para nitrobenzene. So you may assume that you separate a pure para isomer from an for para. So here you can, if the order of the reagent is changed, then there will be production of different substance. So the assumption that separate pure para isomer from an ortho mixer does not apply to any other issue. That means synthesis of 1,4-dibromonitrobenzene from benzene, you can see bromine and iron is reacted and it is formed. Again, one molecule of there is again reacted. That's para dibromogen, 1,4 dibromogen, and there is a formation of 1, 2. Here, the nitro group is as auto-directing. Nitro group will be attached to the bromine. They are attached to the bromine. Separate pure isomer of the reaction can be formed. Now, so in case of methyl bromide, you can see the product of alkylation. The methyl group will be added as a result, and it is reacted with the presence of KMnO4 and heat, then carboxylic acid, okay, benzoic acid. So again, the reaction goes on for the nitrobenzene, okay, benzene along with the nitro group is formed. Okay. There may be chance of product if KMnO4 is reacted, then we can fix beta nitro benzoic acid. But in case of order is changed somewhat, KMnO4 is faster than the H3 is to support, then it will para nitro benzoic acid. There are also two products, para nitro benzoic will be formed. So we have to see when the reaction should be added, depending upon the requirement, the product will be formed. Now, going directly to the nitration, here the electrophile nitro group is formed first from nitric acid, H2NO2. Then NO2 will be forming a electrophile NO2, and there will be another HSO4 and H3O plus. So this nitro group will be added to the benzene, and there will be resonance effect. Okay, see all the pi electrons are circulating, so it will forming a resonance hybrid. So depending on the resonance hybrid, nitrogen will be added, and the formation of the carbocation. And this carbocation direct the proton. In case of sulfonation, SO3H2 is also added, and SO3 group is forming a carbocation. Then hydrogen is removed. Then another from a protonium ion, H plus ion is reacted, and it is forming a SO3H. Next, forming to the halogenation part. In case of halogenation, aluminum chloride in presence of chlorine that forms a carbocation, ClCl2, NCl3. It forms a reactant with the chloro group. With the aluminum chloride, it forms a chlorobenzene. By this way, you can got the product of alkylation. and produces different alkali or aromatic chain substituted benzene ring. Now, can use alcohol and acid. If alcohol is added, then phenol, catechol, resorcinol can be put. Okay. Chemical reaction with the alkene. See, alkene have been like toluene or methyl with, can say. Okay. So generic electrophilic aromatic substitution reaction, you can present Y plus Z minus. So Y will be reacted and Z will be liberated. So let's coming to an important question. Why do substituent groups on a benzene ring affect the reactivity and orientation in the way they do? Electrophilic effects pushing or pulling the electrons by the substitution. So whenever in the electrophile is generated, there will be some reaction pushing and pulling. Pushing means the carbocation will be pushed, and pulling means one H minus one base will be there. They will be pulled that H plus ion. Electrons can be donated, pushed, or withdrawn by the atoms or groups of atom higher, and there will be some induction. So due to difference in electrometer, there will be induction, and there will be a resonance, delocalization of the pi electron via resonance. See, you form here donating groups is forming some delocalization. Resonance donation is going on. Then induction is going on. Then whenever induction is removed, the product becomes stable. Resonance withdrawal and inductive withdrawal. Whenever the resonance and the inductive effect has been done, then it will be stable. It has been electron donated amino chart, which was there. Okay. They will be focusing electron to the benzene ring. Whenever separated, electrons will be donated. An electron withdrawing X means halogen, aldehyde, COR, SO3H, they will be liberating the electrons. Okay. Now, electron donating groups activate the benzene ring to electrophilic substitution. Electron donating group also increases the electron density in the ring and make it more reactive with the electrophiles. Electron donating stabilizes the intermediate carbocation, reverses the reaction and increases the rate of reaction. See, electron withdrawing, deactivating and meta-directing like the CF3, and in case of electron withdrawing, that is deactivating and meta-directing. Electron donating group makes activate the electron ring and it makes orthoparate electron. Okay, so different reactions is there. How to draw resonance structure? You can see here. Now you can find how ortho, beta, and para director are reacting. If G is an electron, donating structures are extremely stable. Again, we are seeing the orthopara, beta, and eta. So, electron donating groups stabilize the intermediate carbocation for ortho and para positions in the electrophilic aromatic substitution than for the beta director. Okay. Same discussion is going on. I think no need to discuss again more. So, again, finally, we can conclude that amino, NHR, NHR, they are the orthopara director and beta director. The reactivity increases along the arrow side. So, thank you all. I think this chapter makes you standing and you have finished study for your discussion.